Now here is a general way to go from the construction for cyclic groups to constructions for groups that are products of cyclic groups. So in general, let's say that we have two groups. Then we can construct their product by defining the product of these two groups as being the group whose elements are pairs of elements, one from the first group and one from the second group, and such that when you want to do an addition operation over the pairs, you just do it component-wise. So for example, if you want to construct the group Z3 times Z7, so this will be the group whose elements are pairs where the first element is a number mod 3 and the second element is a number mod 7. And the way you do operations is to do them component-wise. So you'll compute 2 plus 1 mod 3, which will be 0, and 1 plus 4 mod 7, which will be 5. Now let's say that we have constructed a product group A times B, and that we knew some character F for A and some character G for B. Then just by defining the mapping that takes the pair AB into F of A times G of B, we construct a character for the product group. It's easy to verify that all the properties of characters are true for this construction. So this gives us a way to construct all the characters of all the abelian finite groups. But there is a theorem that now we'll give just without proof, that if you have an abelian finite group, it's always possible to write it up to isomorphisms as being a product of cyclic groups, where these numbers n1 through nk are numbers whose product is the cardinality of gamma. Put these results together, we see that if we take any group that is abelian and finite, we can decompose it into a product of cyclic groups. Now each cyclic group has characters given by that mapping of an input x into e to the 2 pi I times a times x divided by n, where a can be chosen from 0 through n minus 1, and each choice determines the character. So now a generic character of Zn1 will be given by the choice of a number a1, and then the corresponding character will map x1 into e to the 2 pi I a1 x1 divided by n1. Now you can do the same for each of the groups, and then you can apply the product construction, and that will tell us that for every choice of a1 in the group Zn1 up to ak in the group Znk, we can define a function that on input x1 through xk will give this output. And this function will be a character for the group gamma. Now the number of choices for this function is n1 times n2 times nk, which is the cardinality of gamma. So that gives us all the possible characters of the group gamma. To see an example, let's go back to the way we thought about the hypercube as a Cayley graph. So there the group was the set of all binary strings of length d, and the operation was the bitwise XOR. To view this group as a product of cyclic groups, we can see it as being the product of d copies of the cyclic group Z2. That's the group that has only the elements 0 and 1, and when the operation is addition mod 2, which is the same as XOR. So what are the characters of this group? For every choice of bits a1 through ad, we have this function that maps d bits x1 through xd to this output, and that's since e to the pi I is just minus 1, this is just minus 1 to the power of summation over j of aj xj. Now, the reason why we defined the notion of a character was to simplify the computation of eigenvectors and eigenvalues. So let's say we have a Cayley group, and that A is the adjacency matrix of the graph. Let's also suppose that F is a character of the group gamma, and let's think of F as being a gamma dimensional vector, such that the entry x of this vector is f of x. In general, one can always think of a function defined over a finite set of k elements as being a k-dimensional vector, where the entries of the vector are the same as the inputs for the function, and then the content of the entries of the vector is the same as the outputs of the function. So under this view, what is the matrix A multiplied by the vector f in position v? Well, applying the definition of multiplication of a matrix by a vector, this will be summation over u of AVU times FU. Now the matrix AVU is 1 when VU is an edge and 0 otherwise. And VU is an edge if and only if V minus U is in S. So we have this equality. Now what does it mean that V minus U is in S? It means that we can write V minus U as being equal to some group element which is in the set S. So this also means that U can be written as being V minus S for some element of the set S. So this summation can also be written equivalently as this summation. Then we can also recall that the set S has the symmetry such that minus S is in the set if and only if plus S is in the set. So this is also the same. Now we can apply the definition of characters and pull f of v outside. So now the vth entry of the vector A times f is the same as the vth entry of the vector f times this number. So this means that f is an eigenvector of the matrix A, and that this number is the corresponding eigenvalue. Now A is a gamma by gamma matrix. Each character is an eigenvector. Different characters are orthogonal. We have cardinality of gamma characters. So we have found all the eigenvectors of the matrix. And for each of them, we know what is the corresponding eigenvalue. So all the eigenvectors of the cycle are of this form, and the corresponding eigenvalue is just this number. Now we expect the eigenvalues of the adjacency matrix of the cycle to be real numbers, because the adjacency matrix of the cycle is a symmetric real matrix, so all its eigenvalues must be real. And in fact, if we expand what this number is just the cosine of the exponent except with I plus I times the sine of the exponent without I. And the same here. Then just trigonometry, this sine and this sine cancel out, while these two cosines will add up. And so those are the eigenvalues of the adjacency matrix of a cycle. 2 cosine of 2 pi a over n, where a is allowed to range from 0 through n minus 1. Those are the n eigenvalues of the cycle. When a is 0, cosine 0 is 1, so the eigenvalue is 2. And when a is 1, we get the second largest eigenvalue of the adjacency matrix, which will be 2 cosine of 2 pi over n. Now the cosine of a small number is close to 1, and the cosine of epsilon is roughly 1 minus epsilon square. So that's what this second largest eigenvalue of the adjacency matrix is going to be like. Now from the adjacency matrix, we pass to the Laplacian by this transformation. So every eigenvalue of the adjacency matrix becomes an eigenvalue of the Laplacian if you look at 1 minus half times the eigenvalue. So the largest eigenvalue of the adjacency matrix will become 0, the smallest eigenvalue of the Laplacian. And the second largest eigenvalue of the adjacency matrix will become the second smallest eigenvalue of the Laplacian, which will be order of 1 over n squared. So lambda 2 of the Laplacian in a cycle is order of 1 over n squared, but the expansion is 2 over n. And so this means that we have a tight example, at least up to constant, for the upper bound in Cheeger's inequality. let's say that the expansion is at most the square root of lambda 2. Now let's do a computation for the hypercube. So in the hypercube, the group has the following characters, as we computed before. And set S is made of all the strings that have exactly 1, 1. So now to compute the eigenvalue corresponding to this eigenvector, we have to sum the outputs of this function over all the choices of x1 through xd as being of this form. So for example, what is this when we pick x1 through xd to be 1, 0, 0, 0, 0? Well, this summation will just be a1. The whole thing will just be minus 1 to the a1. Then we have to sum the output of this function on input 0, 1, 0, 0, 0. So this will just be minus 1 to the a2 and so on. So the eigenvalue corresponding to this eigenvector will just be summation over I of minus 1 to the ai. And so what is this? It's the number of zeros in A will contribute 1, and each of the ones in A's will contribute minus 1 to the summation. So the largest eigenvalue, those are still eigenvalues of the adjacency matrix of the hypercube, will be the one where all the AIs are all zeros. So this summation will be D. And the second largest will correspond to the choice of A1 through AD, which has the fewest number of ones. They have just 1, 1. So each of them, when you compute this expression, will give you an eigenvalue of D minus 2. Now when we look at the eigenvalues of the Laplacian, this will be the smallest eigenvalue of the Laplacian, will be 0. And this will be, with multiplicity D, the second smallest eigenvalue of the Laplacian, which will be 2 over D. So in the hypercube, lambda 2 of the Laplacian is 2 over D, but the expansion is 1 over D. So that's a tight example for the easy direction of the Cheeger inequality. And here it's actually tight, not tight within a constant factor. Now, what are the eigenvectors of lambda 2 in the hypercube? Because we said that lambda 2 in the hypercube had high multiplicity, had multiplicity D. So if we call EI the Boolean vector that has 1 in the ith position and zeros everywhere else, then each of the eigenvectors, or each of the characters chi EI, is an eigenvector of the eigenvalue lambda 2 equal 2 over D. So also any linear combination of those vectors is an eigenvector of lambda 2. Now let's look at their sum. This is still an eigenvector of lambda 2. Now what is this eigenvector? What value does it associate to every vertex of the hypercube? If we think about it for a minute, f of x will just be the number of zeros in x minus the number of ones in x. So what happens if we apply the sweep algorithm to this eigenvector of lambda 2? Well, then the vertices will be sorted according to the number of ones that they have. So then the best cut that can be found if the vertices are ordered in this way, it's the cut where you get all the vertices that have a majority of ones on one side and all the vertices with a majority of zeros on the other side. And that's not the least expanding cut of the hypercube. This is a cut that has expansion roughly 1 over the square root of D, while the optimum is 1 over D. So this is an example of the fact that if you just give an eigenvector of lambda 2 to the sweep algorithm, you're not guaranteed to find the optimum. You might find some solution that could be as bad as being the square root of the optimum. But that matches the analysis of the algorithm when you say that the value of the solution found by the algorithm is at most square root of 2 lambda 2, and then lambda 2 is at most twice the optimum. So the quality of the solution that you find is order of the square root of the optimum.